Battery anxiety ends here. Tesla's Model 2 hits 80% charge in just 12 minutes at 180 kilowatt stations, a 55% time cut over conventional lithium packs. The secret? Aluminum-ion chemistry, delivering 25,800 cycles with only 7% degradation while you drive 325,000 miles. How does a sub-$15,000 EV charge faster than premium models costing triple? This breakdown exposes the electrochemical engineering behind Tesla's 12-minute miracle and why every competitor is now scrambling to catch up. Here's the 12-minute charging reality broken down. Tesla cracked aluminum-ion chemistry where others failed for decades. Lab-validated testing shows 25,800 cycles with just 7% degradation over the battery's lifetime. That translates to 325,000 miles of driving before you see any meaningful capacity loss. Lithium-ion packs and comparable EVs start fading around 1,500 cycles, then accelerate towards 78% capacity after repeated heat exposure. Why the massive gap? The electrochemical structure handles high discharge rates without the thermal runaway risks that plague lithium chemistry. Let's talk numbers that matter. The Model 2 packs 42 kilowatt hours, nominal capacity delivering 370 miles EPA range, in a module weighing just 330 pounds. That's 370 watt-hours per kilogram energy density, which is 32% more compact than conventional lithium packs at equivalent range. Tesla saves $220 per vehicle in frame reinforcements because engineers don't need to build massive structures around a smaller battery. You're getting more range, less weight, and lower manufacturing costs simultaneously. How often does that equation work out in automotive engineering? The charging curve is where physics gets rewritten. Proprietary algorithms push 180 kilowatts DC into the pack, hitting 80% replenishment in 12 minutes flat. That's a 55% time reduction versus entry-level lithium packs requiring 25 to 27 minutes for the same charge level. Internal resistance measures 10% lower than standard cells, which means consistent power delivery without voltage sag. When you're on your third rapid charge of the day, lithium packs start thermal throttling and limiting output to prevent damage. Aluminum-ion chemistry maintains full 330 kilowatt discharge rates because the fundamental chemistry doesn't generate the same heat buildup. Field testing in California's Central Valley exposed prototypes to 9,000 heat-soaked cycles at 120 degrees Fahrenheit ambient temperatures. The packs maintained 95% capacity after months of abuse that would cripple lithium alternatives. This isn't laboratory conditions where everything is controlled and perfect. This is summer heat turning vehicles into ovens, repeated fast charging sessions back-to-back, and zero maintenance intervention. The aluminum-ion cells barely registered the stress, while comparable lithium packs dropped to 78% capacity and started triggering thermal management warnings. Now here's the twist nobody saw coming. Tesla isn't positioning this as premium technology reserved for high-end models. The Model 2 starts at $13,900 through optimized supply chains and manufacturing efficiency. High-pressure die casting for motor housings dropped costs 42% per assembly. Rare earth-free magnets eliminate supply chain vulnerabilities while cutting $420 in component expenses. The company is manufacturing 750,000 units annually with 32% profit margins, independent of fluctuating tax credits. They're not subsidizing this breakthrough. They're industrializing it at scale that makes competitors' research budgets look insignificant. But does faster charging mean anything if the car can't deliver on performance? The dual motor architecture proves otherwise. The front motor pumps 155 horsepower and 210 pound-feet of torque for precision urban efficiency. Internal dyno testing reveals 22% better low-end efficiency in city driving loops, minimizing battery drain by 12 kilowatt hours per 100 miles versus single motor setups. You're not burning through that fast charging advantage every time you accelerate from a stoplight. The rear motor adds 185 horsepower and 230 pound-feet for highway overtaking power, pushing combined output to 385 pound-feet of torque. That enables 0 to 60 miles per hour launches in 5.8 seconds, while maintaining 5.0 miles per kilowatt-hour highway efficiency. How is an affordable EV delivering sports sedan acceleration without destroying range? The torque vectoring system is the hidden weapon. Real-time power allocation algorithms redistribute torque to individual wheels, improving dry pavement grip by 18% and reducing understeer by 37% in wet conditions. Skid pad testing hits 0.92 G-forces, showing a 22% edge over similarly priced hybrids that cost more to operate long-term. When roads turn treacherous, the system adjusts in milliseconds using sensor fusion with onboard IMU, data for 15% improvement in yaw rate control. You're getting stability engineering that used to require $50,000 performance packages, now standard in a vehicle costing less than a used Camry. Senior mode integration reveals Tesla's broader strategy. The system modulates torque curves by 16% for smooth departures that reduce acceleration-induced discomfort. Biomechanical analyses show 24% reduction in muscle strain during extended highway driving, which aligns with senior mobility research indicating 78% of older drivers prioritize comfort over raw speed. Predictive algorithms conserve 12% more energy for extended trips, while telemetrics provide proactive health diagnostics before issues develop. This isn't just about making EVs accessible, it's about making them preferable for demographics that traditionally avoid electric vehicles. The regenerative braking system recovers 32% of kinetic energy in stop-and-go traffic, adding 55 miles to range estimates during urban commutes. That's the difference between making it home or hunting for a charging station during rush hour. Operational costs calculate to $0.018 per mile based on EIA regional fuel averages, which represents 65% savings over mid-size gas sedans. You're spending less monthly on electricity than most people spend on coffee, while driving a vehicle that outperforms competitors, costing twice as much. Manufacturing scalability backs up the aggressive pricing. Assembly line optimizations, including robotic welding for motor mounts, reduce build time by 20 minutes per vehicle. Tesla projects ramping to 1 million units by 2027 without quality compromises, which would make the Model 2 the highest volume electric vehicle in production globally. The competition isn't just behind on battery technology. They're behind on manufacturing efficiency, supply chain integration, and cost structure by margins that require years to close even with unlimited budgets. Against the Chevy Bolt EUV, the Model 2 delivers 15% quicker quarter-mile times at 14.5 seconds, while consuming 10% less energy in mixed driving cycles. That's not marginal improvement. That's a different vehicle class wearing an entry-level price tag. The Bolt uses conventional lithium-ion, requiring 27 minutes to 80% charge, and showing capacity fade after 2,000 cycles. The Model 2's aluminum-ion chemistry will outlast the vehicle's structural components before needing replacement. What happens to the used EV market when buyers realize some batteries last 3 times longer than others? Here's the evaluation nobody's discussing. Tesla just eliminated the primary objections to EV adoption simultaneously. Range anxiety? Gone with 370 miles in 12-minute charging. Performance concerns? Demolished with sports sedan acceleration and handling. Affordability barriers? Removed at $13,900 starting price. Battery longevity worries? Erased with 25,800 cycles proven in field testing. The Model 2 isn't competing with other budget EVs anymore. It's competing with the entire used car market for drivers who need reliable transportation without premium pricing. The implications extend beyond individual purchase decisions. If aluminum-ion chemistry proves this durable at scale, resale values on lithium-based EVs could crater within 3 years. Why buy a used EV with degraded battery capacity when new vehicles offer triple the lifespan? Fleet operators are already calculating total cost of ownership over 300,000-plus mile life cycles, where the Model 2's battery outlasts multiple vehicle replacements. Municipal governments considering EV transitions now face procurement decisions where upfront costs matter less than decade-long operational savings. Which advantage matters most for your situation? The 12-minute charging that eliminates road trip anxiety? The 325,000-mile lifespan that outlasts conventional ownership cycles? The sub $14,000 price that competes with used vehicles, or the performance metrics that embarrass cars costing triple? Drop your priority in the comments because the conversation around EV adoption just fundamentally shifted. This is exactly why traditional automakers are panicking. Tesla didn't just improve charging speeds. They fundamentally rewrote battery economics. When aluminum ion delivers 325,000 miles at $13,900, every lithium-based EV becomes obsolete math. The question from our opening wasn't whether 12-minute charging is possible, it's whether the entire industry can pivot fast enough before Tesla owns the affordable EV market completely. This breakthrough extends beyond personal transportation. Municipal fleets, delivery services, ride-share networks. They're all calculating life cycle costs, where battery longevity matters more than sticker price. When one vehicle's battery outlasts 3 conventional replacements, procurement strategies collapse overnight. We're watching the transition point where EVs stop being alternatives and become the default rational choice. And this is just the beginning. Tesla's manufacturing ramp targets 1 million Model 2 units by 2027, which would flood the market with vehicles that charge faster and last longer than anything currently available. Competitors have maybe 18 months to respond before market share becomes unrecoverable. The aluminum-ion chemistry isn't proprietary forever. Expect licensing deals or desperate R&D acceleration across the industry. How do you think legacy automakers respond to this? Do they license Tesla's technology, accelerate their own solid-state programs, or double down on hybrids? Drop your prediction below because the next 24 months will define who survives the EV transition. This is Tesla Zone, and we break down the engineering that separates hype from reality. For the latest developments in EV technology and manufacturing innovation, you know where to find us. The battery anxiety era just ended. What comes next will be even more disruptive. The Tesla Model 2 just landed with panels that repair themselves. A scrape in the parking lot? The aluminum flexes, absorbs impact, and returns to normal. No body shop, no repainting, no insurance claim. Tesla engineered 6000 series aluminum alloy with 14% more elasticity than anything else on the road. How is every other car maker still selling cars that dent permanently? These panels save owners $180 to $450 yearly on repairs that simply won't happen anymore. The technology isn't coming. It's here, mass-produced, street-legal. Can the industry catch up? Most electric vehicles have a dirty secret. They overheat under pressure, push them hard on a highway, demand rapid acceleration, or drive through summer heat and watch the performance warnings light up. Tesla's answer? A front grille that thinks. The Model 2's active airflow shutter system opens and closes in real time, making split-second decisions about when your car needs to breathe. When the battery heats up or you're cruising at high speed, the grille opens like a valve, directing airflow exactly where thermal stress is building. Then it closes the moment cooling requirements drop. Why does this matter? Because with the grille closed, aerodynamic drag drops by 0.05 to 0.01 coefficient. That translates to 5 extra kilometers per charge and 4% better energy efficiency. While competitors add bigger, heavier, more expensive batteries to squeeze out range, Tesla just designed smarter airflow. No extra weight, no cost inflation, just applied physics. Here's what the press releases won't tell you. This system keeps internal temperatures 5 to 7 degrees Celsius lower than conventional designs. Battery degradation is directly linked to heat exposure. Every degree matters when you're talking about a $15,000 battery pack that needs to last 300,000 kilometers. The Model 2's thermal management isn't just about today's drive. It's about whether your battery is still viable in 2035. Can your current EV make that promise? The performance implications are immediate. Constant torque delivery, no power fluctuation during overtaking, traction control that